Welcome to the course on two-dimensional signal processing, principles and practices. We had done the overlap add and overlap save methods for computing the convolution of larger sequences in both 1D and 2D. So we have also done the 2D DFT, and practically performing the 2D DFT for a computationally efficient purpose, it is done through the FFT. So Fast Fourier Transform. So first we will do the 1D FFT, just a review of it, and then how do we use this 1D FFT in the case of 2D FFT. So FFT, Fast Fourier Transform, we know this divide and conquer rule of this algorithm, that FFT is the high efficient one, which is computationally efficient compared to DFT. We have seen this n complex multiplication and n minus 1 complex additions for 1k in DFT, and whereas for n such k-bin indices, it's going to be n square and additions will be n into n minus 1. So as the order of n increases, this would become more complex, so the FFT complexity is less. And the order of n square, as I told in the DFT, now this is reducing to odd order n log n. So the order is now reduced to n log n. This is used in the real-time processing for computational complexity reduction. Now, one thing we need to know, this FFT, a very basic thing, that what is bit reversed 1 order. So here if n is 0, in binary we represent it as 000, and bit reversed is also represented here. This is also 0, where we didn't change anything in the 0 case, that it is bit reversed. When we take 1, we can observe the difference, that binary is represented in 3 bits 1 here, and if you bit reverse it, that is putting this last 1 here and this, and just reversing the order. So this becomes 4 now. So the 1 become 4. The similar thing can be followed for other values as well. This 2, let us take 2, there is no, in the bit reverse it would be 2 only, and 3 would go to 6, 3 would become 6. Okay, so 6, and 4 becomes 1, so you can see this is changing here. Okay, here, and then 5 is same, and 6 is going to be 3, and 7 is becoming 7 only. So this is 8-point FFT. You can change it to any order n also. So now, to know the bit reversed 1, this is the way in which done. So there are two types, as we know, that FFT can be, and then DIT algorithm and DIF algorithm, decimation-in-time and decimation-in-frequency. Radix 2 is very common, and it can be extended to other radix as well, radix 3 and also. So DFT equation is known, xk, that is the each bin index for k varying from 0 to n minus 1, the x of n samples of computed for n point DFT, the summation is over e power minus j2 pi k n by n. So this DFT equation as the basis, we are going to derive the FFT from this. Okay, so first we have this x of n samples to x 2n samples and 2n minus 1 samples. That means separating them into even and odd samples. Okay, so now this n is now replaced. It's a 2n, you can see in this, and here n is replaced with 2n minus 2n plus 1, and that plus 1 is taken over here. Okay, so that's how this together performs this as 2n plus 1, the same one. But if you look at the summation, then once you divide it into even and odd, 8 samples are there, and 4 and 4 samples, then that 4 samples should be considered in this one, and another 4 samples should be considered in this another summation. So what we have is 0, n should be from 0 to n by 2 minus 1, not up to n minus 1. So this is the two summations, it is divided 0 to n by 2 minus 1. So this is how first division takes place. Further we will take each of this and then further divide it to n by 2 to n by 4 and n by 2 to n by 4. So that's how it goes, as smaller as possible, that point DFT. Suppose we have this 8 point and then divide that into 4 point DFT and 4 point DFT, and then further dividing into 2 point, 2 point and 2 point and 2 point. So that will be that total 8 point DFT can be computed. So this is how the algorithm goes, and here we know the Tudel factor w suffix n is e power minus j2 pi n, and with this background that we just simplify this e power minus j to 2 pi by n k, we just replace it with w suffix n. Okay, so w suffix n and 2n k from here, 2n k, and similarly the x2nk is also here we have done wn2, and this also has made wn. Okay, so the total factor is replaced for the e power minus j2 pi by n. Now for the simplification, that what is the wn square? Okay, so wn is e power minus j2 pi by n. Then what is the wn square into 2 would result in e power minus j2 pi, and this 2 can be brought in division n by 2, and so we can write this wn square wherever it is, so in terms of wn by 2, so w suffix n by 2. Similarly here this square has come down here, n square by 2, so this is the common way to write this 2, and we kept this as such, so this rest of the summation remains same. Okay, and two n by 2 summations can be combined to make n point DFT. This is one 4-point and one 4-point DFT. But if we take using the periodicity, if we know that redundancy of the DFT, so x of k and x of k plus n by 2, we take it, and then this k is now added with the k plus n by 2 terms. Okay, in that case what we get is 2n, and now k is replaced everywhere to k plus n by 2. We see in the previous case k plus n by 2, and this is k plus n by 2 again. So the rest of them are remaining same, and this k is also replaced with k plus n by 2. So how can we simplify these terms further? So if we take this w suffix n by 2 and that n into k plus n by 2, where this multiplication, this is first term from here, and n multiply with the second term would result in this n into n by 2. So the first term is such we cannot do any further reduction in this, and in the case of this one, if we expand it, w n by 2 in w e power minus j 2 pi by n by 2 into n by 2, so this 2 gets cancelled, this becomes 1, right? This is becoming 1, so we can simply replace this with 1. So the whole term now getting into this term w suffix n by 2 into nk, so simply. So similarly this one w in k plus n by 2 can be again further, these two terms we are trying to reduce it further. This wnk one term and wn by 2, this is another term which is coming out from here. So what is this going to be? E power minus j 2 pi n by 2n. Okay, so here this is n2, and what we have is this minus 1, so n and 2 to cancel, e power minus j pi, so which is nothing but minus 1. Okay, so this is going to be minus wnk. So now this equation k plus n by 2, this term is becoming minus, okay, and this is becoming wn by 2 nk as we did in the previous equation, that is x of k. So now taking these things into this into the equation, so this becomes minus wnk and x2n nk by 2, and the same. What is the difference between the first equation and the second equation? Is one, this wnk is plus, and whereas that one is wnk is minus. Okay, so xk equation we get this xk plus n by 2 is having the equation. What is the k varying from? So this is varying from 0 to n by 2 minus 1. So we have this 4-point and 4-point DFTs computed from these two equations. So now the x of k is splitted into two equations. One is having the x of k of 2n samples, 2n plus 1 samples, 2n and 2n plus 1 samples, and the k plus n by 2 also. So completely two equations now describing the DFT equation, which is x of suppose it is 8-point DFT, 0 to 7 points, we would get it from here. So just splitting that time domain samples into even and odd and performing the 4-point DFTs and varying the k from 0 to n by 2 minus 1 in this fashion, we will get x of 0 to x of 7. So can we further divide to 4-point DFT? Further smaller DFTs can be done on that. So this we have as call this as g of k, this DFT, the whole thing, this is a DFT, and there is a factor, total factor, and then we call this DFT and n plus 1 DFT as hk, and this is same as this is also gk, and this is again hk. So now if we consider gk and hk, can we further divide that into the DFTs of n by 4 or n by 4 DFT? So getting into that, whatever we have done so far, that is x0, 1, 2, 4, 6, that is even samples and then odd samples have been taken, and compute the 4-point DFT, which results in 0, 1, 2, 3 of G and H0, 1, 2, 3 here. And that is having the W80, that in the equation what we had, WN K. So that's what we get it here, x sub 0, and W80 is multiplied, here W81 is multiplied, and W82, W83 and so on. This x G0 and H of 0 and G1 and adding it with H1. So G2 and adding with H2 gives us an x6 and x7. So here x0 is obtained, G0, H of 0 into W80 plus, that is the equation. X1 is G1 and W81 into H1, result in x of 1. So in this fashion we can get through the, here also we can stop, that is we have this even and odd, and we can get this x of 0, 1, 2, 3, 8-point DFTs. Can we further dividing this into 4-point DFTs, that is computed from 0 to 3, 0 to 3. Is it possible to do that? So that's what we are going to do it again. This 4n and 4n, that is 4n and 4n plus 2, that is 2n and 2n plus 1, those samples are further divided into 4n, and here it is 4n plus 2. So we get, and k plus n by 4, as we did x of k and x of k plus n by 2. So here g of k and g of k plus n by 4. So now this is n by 4 minus 1, that is 8. Here is 2 minus 1, this is only 1, 0 and 1. 0 and 1 summations vary. So we have the 2-point DFT. This whole thing now split into 2-point DFT. So all GK can be obtained from this 0, 1, 2, 3, 4 of k. So this is varying for 0, 1, 2 to n by 4 minus 1. So that is 0 and 1 only here. So we get all G's, and all H similarly can be obtained from that as well. So now further, this is called AK, the DFT is called the AK, and this is BK, and we can name it any of the alphabets using that. And getting H of k, similarly the bottom of the samples in the image. So HK plus n by 4. So we get the difference between this forms a butterfly structure, n by 2k and minus wn by 2. So this is AK, and here we had AK and BK, and this H of k is CK and DK here. Okay, so this is 4n plus 1 and 4n plus 3. So that 2n plus 1 point is further divided into these divisions. Okay, so what we have this now is the 2-point DFT. So give this 0, 4, 2, 6, 1, 5 and 3, 7. These samples, you can see among the even sample we have further divided into even, and then among the odd samples we have further divided into this. So now we get this bit reversed order. You can see that bit reversed order, 0, 2 is 4 and so on. So this way you give this samples as bit reversed 1 and get the samples as here x0 to x7. So in the DIT. So now compute this 2-point DFT of this A0 and A1 obtained it, B0, B1, C0, C1, B0, D1. So 4 2-point DFTs, and from that W40, the equation twiddle factor multiplying that butterflies 0, 1, 2, 3 of G and that stage, and the next one is H of 0, 1, 2, 3. So we can obtain these things, and the output also can be obtained from the first stage. So this was the first stage, and then second stage, and this is the third stage. Now this 2-point DFT, just simply we are going to replace it with the butterflies. So that is having 1 and minus 1 in the A and BK. So 0, 1, 0, 1, 0, 1. So this is a complete DIT algorithm, in which if we take n as 8 point, make it in power of 2, because we have chosen radix 2, and otherwise it should be if radix 3, then it should be 3 power something. So you can have that in that fashion. Suppose 9 3 square. So if it is radix 3, so the same butterfly can be done for radix 3 as well. So number of butterflies per stage if we take this stage, this has 4 butterflies. Okay, so this is one butterfly. The two equations containing gk and gk and gk plus n by 4 are xk and xk plus n by 2. So ak and bk, and similarly ck and dk. So these things would form a one butterfly. So each stage will have the 4 butterflies here. This is 1 2 3 4 butterflies, and here 4 and here 4. So 8 by 2. So the butterfly counting is this with the whole thing here. If x0 and x4, what we have is the butterfly. This is one butterfly, and similarly here we have 1, and this is 2, and this one and this one here 4. So each stage has 4 butterflies. That is going to be n by 2. If you have n point DFT, 8 by 2, that is 4 butterflies we'll have in each stage. So number of stages, how do we calculate? That is log base 2n. So n is 8 over here. That is the 3 stages, 1 2 3 3 stages. First we had this 8 point DFT with 4 point and 2 point. So this is how it becomes 3 stages. And what are the complex multiplications and additions required? Okay, so complex multiplication, the log base 2n each stage into n by 2, that is each butterfly will have this one complex multiplication, that is wn0. You can see here one complex multiplication and 2 complex additions. Okay, so that's how it becomes n log base 2n and n by 2 log base 2n. So this is about the DIT algorithm. And if we use the DIF, that is decimation in frequency, we have done the previous case, decimation in time. You can see the samples dividing in the time domain. Okay, now can we divide the samples in the frequency domain? That is like so we can xk, these samples can be divided to the frequency domain. So this 2n plus 1, what we did in the time domain, we will do it in the frequency domain, x2k and x2k plus 1. So in that fashion, what we do the decimation in frequency. So now the DFT equation is this, it's known, and samples, this is n point DFT. Now split this summation n varying from 0 to n by 2 minus 1 and n by 2 to n minus 1. So this is the 8 samples, suppose n point 8 point DFT. So 0 to n by 2 minus 1 and n by 2 to n minus 1, splitting in that fashion, not even and odd. Okay, so the x of k is first n by 2 samples and next n by 2 samples are divided. And so if you take this n can be next to n by 2 samples can be written in terms n plus n by 2. So the summation remains same like this. So this can be written in this fashion. So n is replaced with n plus n by 2 here. So now this is the x of k equation. So now making this x of k equation, varying that is twiddle factor 1, will have, simplifying it, n by 2, wn n by 2 k is e power minus j 2 pi by n in k into n by 2. So this is what here. So this is minus 1 per k. Okay, so here this gets cancelled and e power minus j pi k, so which is minus 1 k. And so we can simplify this as x of n. This is going to be here wnk and wnk, which is common, and the samples, these are x of n and x of n plus n by 2, but this term is getting simplified to minus 1 power k. That's what. So now this is the simplified equation of this x of k, that DFT equation. Now we do this decimation. So if we do k, replace this k with 2k, then here also it becomes 2k. That's the only difference. And then 2k equation, if we this is varying, so this becomes positive, this k equal to minus 1. And similarly for a 2k plus 1, we take this for 2k plus 1, in that n is varying from n by 2 minus 1. So we have this odd samples is 2k plus 1 cases. We will get the negative if we simplify it. So this becomes a negative wn and wn xn minus xn and n by 2, whereas in the 2k equation this is becoming positive, and there is a twiddle factor multiplied in the x of 2k plus 1. So this is decimation in frequency. So these two things, g1, that is from the previous x of 2k, and g2 from the x of 2k minus 1. So this one including this would form g1 and g2, Okay, these two forms a butterfly. So we can take the x1 and x1, add it, and then xn minus x minus 1 multiplying by total factor would give the butterflies here. So taking the DFT of this, so x of 0, so you can see we have not given the bit reversed order. So in DIT, you have to give it in the bit reversed order, that is even and odd. So this is given as such in the order. The decimation is done in the here 0, 2, 4, 6 and 1, 3, 5, 7 like that. So you get G10, that is the previous slide we had these explanations about what is this equation is. You can see the total factors coming in and then pass it to the 4-point DFT, get the DFT here. So can we further divide this into 2-point DFTs? That's what then the next step in the decimation. So take G1K, that's what we had, G1 and G1 here, and then this can be written like that as we did in the first step of x of k, and only this n by 2 would be changed to n by 4 to this n by 4 minus 1. So we have the, so to make the summation same, we have G1 n plus n by 4. Okay, so now minus 1k, which is divided this part, make it minus 1k like in the previous case. So we get G1 2k, decimate it, the G1 into G1 2k and G1 2k plus 1. So this is one portion of G1 alone, taking it into one butterfly, and this is another butterfly which is making it. So for k is varying from 0 to n by 4 minus 1. So the same thing should be done for G2 as well. So the G2, which is just a change in sequence of G1 and G2 only. So G2, and which has this Wn n by 2 like the one we had in the x2 case. So now coming to the total x0, x1, you can see the splitting of sequences where 0, 1, 2, 3, 4, 5, 6, that is in the order. Okay. And then we get G1 and G2, and here we have this DFTs computed, and then what is the signal? With the signal we can call this as V11 or any of the sequences here, and then pass it to the 2-point DFT, the 2 points over here, each one. So in the like in the previous case of DIT, we'll have the n by 2 butterflies in each stage also, but going from one to another is the difference. So the stage 1 gives this type of butterflies, and then stage 2 and stage 3. Now we are going to replace this 2-point DFT. You can observe 0, 4, 2, 6, 5 and 1 and 3 and 7. So these are bit reversed order DFT what we get. So now we replace this with 1, 1 and minus 1, that is we replacing those sequences as V11 and the V12. Similarly, V21, G2 is now V22. So take this 2-point DFT here. This is the case of same as G2 and G1 cases. Now we have replaced this with the third stage 1 and minus 1, the butterflies over here. So what we get is the bit reversed outputs, but the sequence what we had given is x0, 1, 2, 3, 4 are in the order. So this is the DIF algorithm of FFT, which is very popular and known also for the 8-point DFT with radix 2, the DIT and DIF algorithm. So here you can see the complex multiplications and 4 butterflies in each stage as we did in the DIT algorithm. The computational complexity remains same. So DIF has the bit reversed outputs. So with 1D FFT, Fast Fourier Transform, we had done the DIT algorithm and DFT with the DIF algorithm. So these two FFTs are useful. 1D FFTs are useful for doing the 2D FFT. Like 2D FFT is performed through the 1D FFTs. Like we did in the linear convolution of 2D, what we did is that we have the 1D convolution, two 1D convolutions, row-wise convolution and the column-wise convolution. If the impulse response is separable, that's the second sequence is separable. So similarly here for 2D DFT computation, we did one example of 2D DFT direct computation, and what is the computational complexity of it. And if to reduce the computational complexity, we can go for FFT. But when we do the FFT, we cannot directly do the 2D FFT. So we make use of the 1D FFTs like DIT and DIF algorithms, that what we have done in this lecture, and perform the 2D FFT for computational efficiency, or the improving the computational efficiency, because the DFT has the larger computational complexity. If especially the order of n is large, then the complexity is too much, so we need to reduce it further using the 1D FFT of DIT and DIF algorithms. Thank you.